Welcome everyone. Welcome to today's session, and let's begin with the today's class. Today we have two agendas. Number one, we are going to solve the problems of rotational mechanics, which are asked in UPSC prelims examination so far. Right, and this PDF is given to all of you, which contains the topic-wise questions of UPSC Geophysics prelims. Right, and after that, I will be giving you some work and as well as some lecture on numerical methods. Okay, and that will also is a part of our syllabus, and every year we see the questions coming from it. At least 4 questions or 3 questions are from numerical methods. Okay, so let's begin. So topic is rotational motion, and very simple part of it is if you have watched the lectures, more or less it is the complete or sufficient to solve UPSC geophysics problems. So let's begin. The first question is that the moment of inertia of a rotating body is decreased to 1/4 times its angular velocity, 1/4 times, and its angular velocity is increased to 4 times. What is the kinetic energy of the rotating body? Okay. So few formulas that you know already. Which of them are? So these are the formulas for the rotational motion. Okay. So what are the formulas that we need? Rotational motion. Number one formula that we need is what is angular momentum? Angular momentum is I omega, where I is the moment of inertia and omega is the angular velocity. Is the angular velocity. Okay. Angular velocity is defined as theta by t, where theta is the angular displacement. Angular displacement. How much angle you have rotated? Angular angle you have rotated. Okay. Another formula is for the rotational kinetic energy. Kinetic energy of the rotation, which is given by half I omega square. Okay. So whatever work mass do in linear motion, the same work moment of inertia do in rotational motion. So that is why moment of inertia is mass is the inertia of linear motion and I is the inertia for a rotational motion. Okay. Whatever work velocity do in linear motion, the same work omega do in the rotational motion. Okay. So that is why half mv square becomes half I omega square. Okay. So now what are the data which is given to us? So they are saying moment of inertia is 1/4 and angular velocity is 4 times. Okay. So if I come to the problem, so my moment of inertia has become 1/4 and my angular velocity has become 4 times. Hence, my new kinetic energy half I omega square is nothing but 4 times half I omega square. It means my overall kinetic energy increased by 4 times. That is my correct answer. So it is increased by a factor of 4. So option number B is correct. Yes. Any doubt, anyone? Is it okay to all of you? Perfect. I hope it is clear. Right? Chaliye. So next comes a very simple logic based question. So which is known as a rotational matrix, rotation matrix also you can say. You don't need to remember any formula for that. Just a simple logic will help you in this. Okay. So they're saying that a rigid body rotation in XYZ coordinate is given by this. So you rotate a body and the rotation is given by this matrix. Okay. So this matrix is representing your rotation. So by looking at this rotation, you have to tell ki the rotation is happening around which axis. Are you rotating around Z axis, Y axis or X axis? Okay. So let me write this matrix first of all here. So this is your new coordinates X dash, Y dash, Z dash. They are written in this terms of this matrix, which is 0, 0, 1, 0, 1, 0, and minus 1, 0, 0. And these are your old coordinates X, Y, Z. So let's open this up. Let's open this up. So if I do that, I will get this multiplied by this. So I will get Z, right? And if second row multiplied by second row, this becomes Y. And this becomes minus X. Okay? And this is your X dash, Y dash, Z dash. So from here I can say that my x dash is now z, my y dash is still y, and my z dash is still is minus x. From this I can very clearly see that my y dash is not changing, my y is not changing. It means what I'm doing is I'm holding the y axis and rotating around the y axis so that my y axis don't change and my x and y axis change, x and z axis changes. For example, let me give you this example. Okay, let's say this is your x axis, this is your y axis, and this is your z axis. Okay, if I hold this y axis and rotate, my y axis will not change. This line will remain as such, but you can clearly see that this x will go here, right? It means my x dash will actually become z, and this z will go here, which is negative of x axis. It means my z dash will be negative of x axis. So basically what I'm doing is I'm rotating this by 90 degrees. I am holding y axis and I'm rotating by 90 degrees. If I rotate by 90 degrees, so my x will go to the position of z. X will go to the position of z. That is why you are saying that x dash is z. And my z is going to the position of minus x. Because if you turn this 90 degree in that direction, so z dash will be minus of x. But y axis will remain y axis. Okay? So that is the clear thing here. So the rotation is happening around y axis and the rotation is happening by 90 degrees. Okay? That is why you can see the option number D is correct. So the rotation is happening around y axis by an angle of 90. Okay? So any doubt, anyone? Is it you are able to see the matrix and imagine it? Let me know. Yes. Clear, everyone? Question number 3. What is the moment of inertia of a solid cylinder about its axis? Okay. So you are asked about the solid cylinder about its axis passing through the center of the circular sides is, where m is the mass of the cylinder and r is the radius of the cylinder. So let me first make you these diagram. Okay. So the moment of inertia for a solid cylinder about its axis, which is passing through the center of the circular sides. Okay. So basically, I think the question is not very clear. Center. Okay. So passing through the center means this. Okay, this axis. So what is the moment of inertia around this axis? Anyone? Very good. Very quickly. You must know the table. What is the moment of inertia? B. Yes. So around this axis, the moment of inertia is mr square by 2, and it is same as a disk. Okay? It is same as the disk. That is why option number B is correct. So please remember the tables. What are the moment of inertia of different bodies? Okay. Then comes the next problem. The number of degrees of freedom of a rigid rod of a negligible thickness in 3 space dimension is. What is the number of degrees of freedom of a rigid rod? So you have a rod, basically one dimensional body. So you have a one dimensional body. What is the degree of freedom of this? Okay, what is the degrees of freedom of this? Means how many coordinates you need to completely specify this? What do you think? What do you think? Anyone? Is it 3? Is it 3? Or is it more than 3? What do you think? 5? Okay. 5 is a good answer. Okay. Okay. Let me explain why. So this rod can move anywhere in the space. So this rod can go in x direction, y direction, z direction. So it will have 3 translational degrees of freedom. Now this rod can rotate around y-axis as well as it can rotate around the z-axis. But it cannot rotate around this axis. Why? Because it's a line. You cannot rotate a line. The reason being because the moment of inertia will be 0. Because how do you decide the moment of inertia? Okay. So moment of inertia is defined by the formula summation of mr square. Okay. Okay. So if I'm taking this axis, then it makes sense because if you take any part of the rod, then there is some distance between the rod and this part. So r is there. But if this is a rod and this is the axis, then what is the distance of a rod from its axis? No distance, zero. Moment of inertia is not defined. You cannot rotate the rod around its own axis. In physics, in reality, you can do, because there is no perfect rod, right? You see, there is no perfect rod, because one dimensional rod always have some thickness. But in this, what they are saying is negligible thickness, means it's perfect line. So you cannot rotate a perfect line. Rotation all is always happening for a bodies with some thickness of, because otherwise how do you define the r? How do you define the distance of this rod from this axis? Because the rod is kept on the axis. But let's say rod has some thickness, let's say things like this, then you can say, okay, yes, there is some distance of this point from the axis, right? Then you can rotate around this axis. But if it is a perfect rod, then you cannot rotate around this axis. So you can rotate only around two axes, either this axis or either this axis. Okay, you cannot rotate around this axis. Hence, that is why there are only two rotational degrees of freedom. That is why you also see that the diatomic molecules have 5 degrees of freedom. Similarly, this also has a 5 degrees of freedom. I hope this concept is clear. Anyone, this will have a 5 degrees of freedom, not 6. If you look into the online or internet, they will give you answer 6, but that is wrong. Okay, that is wrong, because they are considering rod as a cylinder. Okay, it's not a cylinder. Thickness is negligible. Yes, any doubt here? Okay. Okay, then comes the question 5, which says a disk of mass m and radius r rotates with an angular speed omega naught. Another disk of equal mass and radius small r is placed on the top of the rotating disk such that their centers coincide. Both the disks now rotate with an angular velocity omega. What is the value of omega? So in such questions, you always use the conservation of angular momentum. Conservation of angular momentum. So initially, there was only one disk which has a mass m and which has a speed omega. Okay. So by the way, what is the moment of inertia of a disk? It is mr square by 2. So this was rotating with an speed omega naught. Okay. And then there was another disk which have the same mass, but the radius is smaller. And this disk was not rotating. This is not rotating. As per the question, this is not rotating. Okay. Then you come and place this disk on the top of the first disk. Okay. So what was the initial angular momentum? By the way, angular momentum is given by I omega. So initial angular momentum is mr square by 2 into omega naught. Now, finally, both the disks are rotating. Okay. And both of them are rotating with an speed omega. So what we can say, mr square by 2 omega plus mr square by 2 omega. Okay. Because now both of them are rotating with the same speed omega. So if you solve this out, what will be the omega? Omega will come out to be capital R square by capital R square plus small r square into omega naught. Okay. So which is going to give you the option number B. So conservation of angular momentum gives you a clear cut answer here. And this kind of question is also solved in the lecture which is given to you. Okay. So what is done here? Conservation of angular momentum before and angular momentum after, you make them equal, and that's all. Nothing else to be done here. Okay, ji? So any doubt here? Option number B is going to be correct, right? Perfect. If you have any doubt, please mention it in the chat box, or even you can unmute yourself and let me know. Okay. Chali. Then comes the question number 6. So two bodies of equal mass m are connected by a massless rigid rod of length 2a. Okay. So two bodies of equal mass m are connected by a rigid rod. So you have a rigid rod which has a length of 2a. Okay. And it is lying in a xy plane with the center of rod at the origin. So center of the rod is origin. If this system is rotating around the z axis, with an angular speed omega. Okay, so let's say this is your axis, z axis, and it is rotating around this axis with an angular speed of omega. Okay, so yeah, that's all. So what is an angular momentum? So angular momentum is again I omega. So what you need to find is I. Whenever you have to find I, you have to make a decision. And what is the decision? Do you have a discrete body? Do you have a discrete bodies, or do you have a continuous bodies? If you have a discrete bodies, means one mass is here, one mass is here, then you use the formula of summation of mi into ri square, where m is a mass of the body and r is a distance from the axis. Distance from the axis. On the other hand, if you have is a basically a continuous body, then you can say it is r square into dm. Okay, integration. Perfect. So this is how you solve this. So in this case, it's a discrete body because one mass is here, one mass is here. So let's take this out. Okay, so let me take the first mass m. What is the distance from the axis? L, because the total distance is 2l. So the distance from the axis is L. So you get ml square plus, then again this mass m. Now what is the distance? Minus L, but the square will be ml square. So the total moment of inertia becomes 2 ml square, and the angular momentum becomes I omega. So 2 ml square omega. So 2 ml square omega is your option, which is correct. So do you all got this the same answer, everyone, or anything else? Everyone got the same answer, 2 ml square omega, right? So this was your question number 6. Very simple question, and these kind of questions are being asked in an exams. Okay, ji? Okay, let's go for question number 7. So again, so what is the moment of inertia I of the thick spherical shell of a uniform density rho with internal radius r and external radius capital R? Okay. Now this is something which is, you can say, is a question from the continuous system. Okay. So what is the system we have? We have a thick spherical shell. Okay. So we have a shell. So let me make this diagram for you. So this is a shell. Okay. So this is a shell, and the shell is something like this. The inner radius of the shell is r, and the outer radius of the shell is capital R. Okay. And you need to find the moment of inertia around an axis. So let's take this axis. Okay. Let's take this axis, and the rotation is happening around this axis. So you have to find the moment of inertia around this axis. Since it is a continuous body, the formula that I will use is integration of r square into dm. Now, it is very important that I use some other symbol so that I don't get confused, okay, with the small r that I have. Now, this r is actually a distance from the axis. This is actually a distance from the axis. Now, what is my work here is to take a small mass. So let's take a small mass. Let me use another pen. So let's take a small mass here. And this small mass is at some distance. Okay. So what I'm going to do here is actually change the notations a little bit so that I don't get confused. Okay. So what I'm going to do is that inner radius I'm going to take is small a, and outer radius I'm going to take is small b, so that I don't get confused. Okay. Okay. Now coming on. So now I'm saying that this small mass is at this distance r, small r, from the center. So is this distance same as this? No, because I need the distance from the axis. So what distance that I need is this distance. I need this distance, and this angle I can call it as a theta. According to the spherical polar coordinate system, you know this is theta. And then what I can say is that, okay, cos theta is given by, what is cos theta? Cos theta can be given by, or you can even use sin theta. So sin theta can be given by this. So hence r is written by r sin theta. Okay, perfect. Now I can put my value in moment of inertia, which will be r square sin square theta into dm. Right. Now, how do you write a small mass? Small mass is a small means density into small volume. And how do you write a small volume in spherical polar coordinate system? It is written by 4 pi r square into dr. Perfectly fine. 4 pi r square into d. So that is what I'm going to use now. So I get r square into sine square theta. Okay. And what I can do actually is I can even, no, don't do this. But you can do here is you can actually write r square sine theta dr d theta d phi. This is much better. Dr r square sine theta dr d theta d phi. This is how you write a small volume in the spherical polar coordinate system. I hope you remember those lectures, and we spent a lot of time in this. Okay, and you can watch my lectures if you are unaware about the spherical polar coordinates. Okay, chaliye, okay. So I will put my value. So this r square sine theta is already there. Now I write the value of dm. So dm is given by rho into r square sine theta dr d theta d phi. ठीक है जी? And then you just need to do 3 integrations. Okay, so let me just separate out those integrations. Number 1 integration is in terms of r. So you get r की power 4, ठीक है, into dl. And now you are going from small r to capital R. If you remember inner radius and outer radius, inner radius is small r, outer radius is capital R. So you are going from small r to capital R. Then comes the second integral, which is sine square theta into sine theta, which is sine cube theta into d theta. And you are going from 0 to pi, right? And the last d phi, which is from 0 to 2 pi. Okay. Now, if you integrate this, you will get r की power 4 minus r की power 4 by 4. This will be little difficult, not that difficult, little bit, but we will do that. And this integration is 2 pi. So first of all, we will check without solving this, can we match an option? So can we match an option without solving this? R4 तो है नहीं किसी में. R4 is not there. So we had r square sine square theta. This is r. Oh, sorry. R4 है ना, तो इंटीग्रेशन करके R5 हो जाएगा, राइट? इफ यू इंटीग्रेट दिस यू विल गेट R5 by 5, है ना? तो इट विल बी R5 by 5. तो either this option is correct or this option is correct. In order to see which option is exactly correct, we need to solve the second integral as well, which is sine cube theta integral. Okay, because that is going to be the biggest challenge. So let's solve this out. So how can you solve the integral of sine cube theta? Anyone got an idea? We have one very simple technique. ठीक है, कैसे करते हैं इसको? कैसे करते हैं देखिए, you can say is it is sine theta into sine square theta into d theta. ठीक है, and then what you say is okay, sine theta को okay, sine square theta को 1 minus cos square theta you can write. Okay, and then you can write sine theta into d theta. ठीक है, what I have done is I have put sine square theta is 1 minus cos square. Now you can say okay, put cos theta as x. It means, and then differentiate, so you will get minus sine theta into d theta equals to dx. It means sine theta into d theta is actually minus dx. Okay, then let's come back. So you get 1 minus x ka square, and sine theta into d theta is minus dx, so minus comes here and dx comes here. Now you can just solve this integral, so you get basically you can take this negative inside, so you get x square minus 1. Okay, so you get x cube by 3 minus x, and then you can just put the value of x back. What was x? X is cos theta, so you get cos cube theta by 3 minus cos theta, and then you can put limits from 0 to pi. Okay, okay, so now if you put pi, so this thing is minus 1, and this thing is 1. Okay, this thing will become minus 1, and this minus minus will become plus. Then minus, then you put 0, so you get 1 by 3 minus 1. Okay, so now let's just solve this out. So you get minus 2 by 3, and then you get plus 2. Okay, so you get 4 by 3. So the value of this integral is 4 by 3. Okay, so the value of this integral is 4 by 3. And then there is this one row which is also there. So just multiply this row here. So now you just need to multiply all these three integrals together. That's all. So what will you get? You get 8 pi by 5. 8 pi by 5. So let's check. 8 pi by 5, we are getting 50. Oh, sorry. 8 pi by 15. Right? 4 into 2 pi, 8 pi, and then 5 into 3, 15. So 8 pi by 50, which is your option number D. Okay? So D option is correct. So this was a continuous body, although this needs more than 1 minute. So they should have not asked this question in this exam. But as such, this is easy question, class 11th based question. So you have a sphere, inner radius small r, outer radius capital R. So first I take is a small mass, you right? And then I use this formula for moment of inertia, which is r square into dm, where this curly r is a distance of a mass from the axis. So this distance. Then I write my small r in terms of curly r. And then I put the value of curly r as r sine theta. Then you know dm, small mass, is density into volume. Small volume in spherical polar coordinates is written like this. So I put this out. This give rise to three integrals. And I solved the three integrals very nicely. And then I just multiplied all of them and I got the option number D correct. Yes. Are you also getting option D, or was that the doubt for you in this assignment? Yes. So there are two spheres, each of mass m. So there are two spheres, you see, one is here and one is here. Both of them has a mass m and the diameter capital R. Okay, diameter is capital R. Okay, so diameter is capital R. It basically means that radius is smaller. Radius is going to be, oh sorry, not smaller, r by 2. Radius is small, r by 2. And they are connected with the massless rod. So both these spheres are connected by this massless rod. The rod has no mass, but the rod has a length 2r. Okay, what will be the moment of inertia of this system about the axis passing through the center of the two spheres? So this passing through the center of one of the sphere and perpendicular to the rod. So this basically. So they are asking the moment of inertia around this. Before you find the moment of inertia around this, what I will suggest you is to find the moment of inertia around this axis. And then you can use a parallel axis theorem. Okay? Okay. So this is very tricky. Very tricky. Okay. Or let's remain in y dash axis. Let's remain in y dash axis, and let me do this question and let me add the page here and let's do it. So in the meanwhile, if someone has already done this question, give your answer so that we can see that if you have done it correctly or not. So these are the two spheres. Okay. And this is your another sphere. Okay. And okay. So let me make equal kind of sphere. Okay. So the distance between them is 2r. And this distance is r by 2 because the radius is r by 2. Okay. And now we are choosing this axis. And we have to find moment of inertia around this axis. Okay. Perfectly fine. Is there any moment of inertia which a rod has? No, because rod has no mass. If the mass of the rod is 0, then the moment of inertia of a rod is also 0. So rod is not going to introduce any moment of inertia in your calculations. Okay, that is okay. Then do you have any moment of inertia of this sphere? Yes. So let's call it as sphere 1 and sphere 2. So moment of inertia of sphere 1 around which axis? Around axis y dash. Okay, is going to be simply, is it solid sphere or a hollow sphere? It is going to be solid because hollow is not mentioned as such. So normal sphere is given. So what is the formula for that? 2 by 5 mr square. But the radius is r by 2. So keep that in mind. Radius is r by 2. Okay. So you get 2 by 5 m r square by 4, which is m r square by 10. Now, what about the moment of inertia of the second sphere around this axis? Let's call it as xx dash. Xx dash. Again, that is also same mr square by 10 because इसका moment of inertia अपनी axis के around mr square by 10 होगा, उसका moment of inertia अपनी axis के around mr square by 10 होगा. But we need the moment of inertia of this around this axis. That is why the moment of inertia of second sphere around y dash will be calculated using the parallel axis theorem. So mr square by 10 plus मास इंटू इन दोनों के बीच का डिस्टेंस का स्क्वायर, वो होगा 2r का स्क्वायर. We know the moment of inertia of sphere 1 around this axis, but we need the moment of inertia of sphere 1 around second axis. That is why we need to use the parallel axis. ठीक है, तो वो हमें क्या दे देगा फिर आंसर, mr square by 10 plus 4mr square, which is going to give me 41.10 mr square. ठीक है, now it is time to find total moment of inertia. So it is 41 by 10 mr square plus this mr square by 10 mr square by 10, ठीक है, which gives you 42 by 10 mr square, which is 21 by 5 mr square. ठीक है, let me see if there is any option like that. Yes, option number A, very good Yash, very good. ठीक है, so this is going to be your correct option. ठीक है, so first I found the moment of inertia of sphere 2 around this axis, that was simple. Then I found out the moment of inertia of this sphere around this axis, okay, and then I converted that into the moment of inertia around this axis, so that I know the total moment of inertia around the second axis. That was the entire question. If anyone have any doubt, please let me know. Right. Anyone? Problem? A wheel is moving due to external force. The time rate of change of angular momentum of the wheel can be maximized by. So we have to maximize dl by dt. dl by dt is nothing but torque. Okay? Because you know force is what? Force is rate of change of linear momentum. So what is torque? Torque is rate of change of angular momentum. So the time of rate of change of angular momentum has to be maximized. So basically torque has to be maximized. What is the formula for the torque? So torque is given by three form. Basically the general formula is R cross F. So either you can maximize the distance from the axis, or you can maximize is the force, or you can maximize is the angle. So applying the force near the axle of the wheel. No. So if you come near, if the force is near, then R will decrease and more or less the torque will decrease. Applying the force near the rim of the wheel and tangent to the rim. Okay. So basically what they are asking is, this is a wheel. Okay. So axle, this is axle and this is a rim. Okay. So if you want to make a maximum torque in this wheel, torque को maximum करना चाहते हैं आप, torque means rotation. तो आपको पहली बात तो फोर्स रेडियली नहीं लगाना है. इफ यू पुट अ फोर्स रेडियली, नथिंग विल रोटेट. यू शुड अप्लाई द फोर्स टेंजेंशियली. Force should be tangent so that the wheel rotates, and also the force should be on the rim, because if the force is on the rim, the distance increases, and if the distance increases, the radius increases. Okay, that is why you see, if you want to rotate the tire, you usually rotate it from the outer end. You don't try to rotate from the center. You don't, for example, fan. If I ask you to rotate the fan, so if you will hold the wing of the fan and rotate, it will be easy to rotate. But if I ask, okay, rotate it from the, hold it from the center and then try to rotate, it will be difficult, right? So you want to increase the torque, so you need to increase the distance. That is why your option number D is correct. Okay. So applying the force F near the rim and in the tangent direction will maximize the torque. And if the torque is maximum, your dl by dt, rate of change of angular momentum, will also be maximum. ठीक है, any doubt in this, anyone? ठीक है, how does the angular momentum of a person change when he spreads his arm horizontally while uniformly rotating on a friction? So you see, if you increase your arm, how will your angular momentum change? It remains the same. Very good. It is known as the conservation of angular momentum. Okay, you see, what will happen is that if you increase your arm, the moment of inertia will increase and angular speed will decrease, but the angular momentum will remain same. Okay, because as long as no other person is exerting torque on you, so if no one else comes and exert the torque on you, your moment of inertia will remain. So this is same as the conservation of linear momentum which we did yesterday. If no one externally is applying force on you, your linear momentum will remain same. Similarly, if no one else externally is applying torque on you, your linear momentum will remain same. You can internally do anything you want to do. Your moment of inertia will not change by that. Oh, sorry, your angular momentum will not change by that. Okay, so that is why it will remain same is the correct option. B option is the correct. Okay. Then comes the 11th problem. Consider the hollow metallic sphere partially filled with sand. So it is half filled with sand and it is shown in the figure. Which of the following points is likely to be the center of mass? कौन सा center of mass होगा? So obviously बात है. Which of them is going to be the center of mass? D is going to be the center of mass. ठीक है? क्यों? Center of mass क्यों होगा ये D? मान लीजिए ये sand नहीं होता. This sand is not there. So D होगा या C होगा? It will be D or C. C. हाँ, C होगा. C is the correct option. The reason being, देखते हैं. So we can divide this thing into two things: empty space and the filled mass. Empty space का तो कोई mass नहीं है. Empty space has no mass. But the filled space have a mass. पहले तो हम सिर्फ filled space का center of mass की बात करें. Filled space के center of mass की. So filled space का center of mass लगभग कहीं यहाँ पर होगा. ठीक है, लगभग कहीं यहाँ पर होगा और ये आपका सेंट्रल पॉइंट. तो जो आपका सेंट्रल पॉइंट है वो इन दोनों पॉइंट के कहीं बीच में होगा, विच इज ऑप्शन नंबर सी. फिर से बात कर लेते हैं. अगर ये सारा का सारा एम्प्टी होता, इफ दिस वाज इंटायरली एम्प्टी, तो फिर मोमेंट ऑफ इनर्शिया कहां होता? ओरिजिन पे. देन द मोमेंट ऑफ इनर्शिया वुड हैव बीन एट द ओरिजिन. बट दिस इज नॉट कंप्लीटली एम्प्टी, इट इज हाफ फिल्ड. तो वेयर इज द सेंटर ऑफ मास ऑफ द हाफ फील्ड? ऊपर वाला भूल जाओ, हाफ फील्ड का सेंटर ऑफ मास है. हाफ फील्ड का सेंटर ऑफ मास लगभग कहीं यहां होगा. ठीक है, तो एक तरह से आप देखा जाए तो अब आपने यहां पर कुछ मास रख दिया, तो आपका योर सेंटर ऑफ मास विल डिविएट लिटिल बिट. तो वो इतना थोड़ी डिविएट हो जाएगा कि वो सेंटर ऑफ मास पे ही चला जाए, तो वो इन दोनों के बीच में कहीं पे होगा. सो दिस विल बी योर ऑप्शन नंबर सी. सो योर सेंटर ऑफ मास ऑफ दिस इंटायर बॉडी विल बी अराउंड सी. ओके, तो ये थोड़ा सा सी होगा. ये दिस क्वेश्चन इज वेरी मच रिलेटेड टू वन क्वेश्चन व्हिच वाज आस्क्ड इन जस्ट. In that case, the water was dripping and you have to draw the graph of movement of center of mass with respect to time. Okay, so you can look for that question if you want. So the option will be C, point C. Chaliye, next question number 12. A sphere, a cylinder, a ring of the same radius. So you have a sphere, you have a cylinder, and you have a ring. All of them have the same radius. Are allowed to roll down simultaneously on an inclined plane from the same height without slipping. Which one of them will reach the bottom first? जिसका moment of inertia will be minimum, inertia whose inertia is minimum, that person will reach bottom first. So किसका moment of inertia सबसे कम होगा? Okay, sphere का moment of inertia होता है 2/5 mr square, which is basically 0.54 mr square. Cylinder का होता है mr square by 2, which is basically 0.5 mr square. और ring का होता है mr square mr square. तो सबसे कम मोमेंट ऑफ इनर्शिया है स्पेयर का, दैट इज व्हाई द स्पेयर विल रीच द बॉटम फर्स्ट. क्लियर? ओके, देन कम्स द क्वेश्चन 13. A slender uniform rod of length L and total mass M and has its rotational axis at the center of the length and is perpendicular to the length, its moment of inertia is. So what is the moment of inertia of a rod? We derived this formula in the class. What is the moment of inertia of the rod? It is 1/12 ml square. ठीक है, you can look at this derivation in the classroom in the lectures. So moment of inertia around the central axis is central axis is 1/12. हाँ, 1/12 1/12 ml square. ठीक है, so that gives you option number B. And the last, number of degrees of freedom of a rigid body. Again, this is covered in classical mechanics. Rigid body के लिए कितने डिग्रीज ऑफ फ्रीडम होते हैं? हाउ मेनी नंबर ऑफ डिग्रीज ऑफ फ्रीडम योर रिजिड बॉडी अराउंड अ फिक्स्ड पॉइंट हैज? अराउंड अ फिक्स्ड पॉइंट, पॉइंट रिमेन्स फिक्स्ड. तो कितने होते हैं भाई बताओ? 3. वेरी गुड. दिस इज अ वेरी वेरी कॉमन फैक्ट इन क्लासिकल मैकेनिक्स. द डिग्रीज ऑफ फ्रीडम, मैं इसके लिए लेक्चर भी दिया हुआ है, विच इज द लेग्रेंजियन का लेक्चर नंबर 1. okay, so degrees of freedom of a rigid body around a fixed point is 3. So that was your question number 14. ठीक है, so yes, that is okay, that is also right. 3 into, yes, 6/2 is 3. Yes, So that was your questions from the rotational mechanics. Okay. Now we will go for the numerical methods, and I hope that you understood the questions we did. 14 questions we did, and that was the idea. Okay. So